All right, today we're going to pull back the curtain on one of the most powerful yet super simple ideas in all of mathematics. It's kind of this hidden rule that makes everything from your phone's security to the internet itself even possible. We are talking about independence in probability. And to really get why it's so important, we first need to understand the massive problem it was designed to solve.
So let's start with this question. Just think for a second about our digital world. It's this universe of just endless connections. Data packets flying everywhere, servers talking to each other. We're talking about trillions upon trillions of interactions happening every single second. So how on earth do engineers build systems that actually work in the face of all that chaos?
Well, the short answer is they don't. They can't. In these huge, complex systems, trying to calculate every single possible outcome, every single dependency, it's literally impossible. The amount of computer power you'd need would be just astronomical. So they need a shortcut, right? A simplifying assumption that just cuts right through all that noise.
So here's our game plan. We've kind of set up the problem of complexity. Next, we'll introduce the simple idea of independence that solves it. Then we're going to dig into the actual math, the rules. We'll uncover a really common mistake people make, see how it all works in the real world, and then wrap up with what I call the engineer's golden rule.
So that shortcut, that really elegant solution, is this concept of independence. You can think of it as the ultimate divide and conquer strategy. It lets us take a problem that seems impossibly huge and break it down into these small, manageable, and, most importantly, solvable little pieces.
So what exactly is it? Well, at its core, the definition is incredibly simple. We say two events are independent if the outcome of one of them gives you absolutely zero new information about the outcome of the other one. Knowing one happened tells you precisely nothing about whether the other one will happen. The classic analogy for this says it all, really. The coin has no memory. If you flip a coin and it lands on heads, and then you go to flip it again, the coin doesn't remember that it just landed on heads. The probability of getting heads on that second flip is still exactly 50-50. The past has absolutely no influence on the future. But, our intuition can be tricky. So to really use this idea properly, we need to go beyond the analogy and get to the mathematical core. So let's take a look at the formal rules that actually define independence.
So how do we prove this with math? Well, we've got a toolkit with 3 core rules. Here they are, all on one screen. Each one looks at the idea from a slightly different angle. But together, they let us prove, without a doubt, if events are truly independent. Let's just let that sit for a moment before we break them down one by one. Okay, let's start with the first one. This is the most fundamental test. That little and symbol, it just means and, or intersection. So this equation reads, the probability of event A and event B both happening is equal to the probability of A times the probability of B. If you can just multiply their individual chances together to get their combined chance, then they're independent. Simple as that. It's the cleanest check you can do.
Now, the second rule frames the same idea, just in a different way, using what's called conditional probability. That vertical bar means given. So P of A given B is the probability of A happening given that we already know B happened. For independent events, this new info is useless. The probability of A doesn't change a bit because knowing B happened didn't matter at all.
And this third rule is so critical when we start scaling things up. What if you have more than 2 events, like A, B, and C? Well, it's not enough for A to be independent of B, and B independent of C. Nope. For the entire system to be truly independent, the probability of all 3 happening together has to be the product of all 3 of their individual probabilities. This is called mutual independence, and it's essential for looking at those complex systems we talked about earlier.
All right, now we have to talk about the number one trap. This is the thing that trips up almost everyone when they're learning this stuff. It's the confusion between independent and mutually exclusive. They might sound similar, but in probability they are basically opposites. Let's just put them right next to each other. For independent events, like we've been saying, one doesn't affect the other. But for mutually exclusive events, if one happens, the other one cannot happen. Think about a coin flip. The outcome being heads and the outcome being tails are mutually exclusive. You can't get both at the same time. Their intersection is empty. There's no overlap.
So here's the crucial point, and I really want you to let this sink in. If 2 events are mutually exclusive, they are, by definition, highly dependent. I know, it sounds totally backward, but it's the absolute truth of the math. And here's why it makes perfect sense. If I tell you the coin flip was heads, that's event A,
What did you just learn about the probability of it being tails, event B? Well, you learned everything. You now know the probability of B is 0. It can't happen. The information I gave you about A dramatically changed what you know about B. And what's our definition of dependence? When one event affects the probability of another. It's a perfect illustration.
Okay, enough with the formulas in the theory for a minute. Let's see how this idea actually plays out in the real world, from our own flawed intuition all the way to the technology we rely on every single day. So picture this. You're at a roulette table. The ball lands on red. Okay. Then it lands on that again, and again, and again, and again. 5 times in a row, it's red. You can just feel it in your gut, right? The next one has to be different.
So here's the question. After 5 straight reds, what is the probability that the next spin is black? Your intuition is screaming that black is due. But the truth is, that roulette wheel has no memory. It's just like the coin. The probability is exactly what it was on the very first spin. Those past spins are totally independent of the next one. Believing anything else is what we call the gambler's fallacy.
And this isn't just about casinos. I mean, engineers build our world on this assumption. In RAID storage systems, they have to assume hard drive failures are independent events so they can calculate the system's reliability. In cryptography, if the bits in your encryption key were dependent, a hacker could find a pattern and break it. With hashing and parallel processing, I mean, the entire design of these things relies on events and tasks being truly independent from each other.
So let's just pull it all together in one quick summary. Independent events are memoryless. The math is just a simple multiplication. Dependent events have a memory or a state, like drawing cards from a deck without putting them back. Every card you draw changes the deck for the next one. This table is a really great way to just lock in everything we've covered. Finally, let's distill all of this down into a set of principles. How do we use this powerful concept wisely and, avoid the pitfalls? This is what I like to call the engineer's golden rule.
Really, it comes down to 3 things. Number 1, verify the math. Never, ever just assume 2 things are independent because it feels right. Always run the test. 2, when you're building things, actively design for independence. You want to decouple your components so a failure in one little part doesn't cascade and take down the entire system. And 3, avoid the trap. Never forget that mutually exclusive events are the very definition of being dependent.
And I'll leave you with this last thought. This isn't just for engineers or mathematicians. We all make assumptions about independence every single day, in our finances, our health, our relationships. So the real question is, where in your life are you assuming 2 things are unrelated, when actually the outcome of one has a very real impact on the other? Thanks for watching.